Hello and welcome to part 1 of a tutorial series on blocking functions in the Python version 2.7 API in Visual Components. Blocking functions halt the execution of a script until a specific event occurs or a certain condition is met. To refer to these functions from the help documentation, visit the Python API section, and under VC script we can find the details on the delay, condition, and trigger condition. The delay function pauses the execution of a script for a specified amount of time and can be used, for example, to pause logic during processing time. The condition function waits until a specified condition is met, and the trigger condition method waits for a specific event to occur, such as a signal. These functions are used to move a servo to a specified position, and the script execution is paused until the servo reaches that position. When following any tutorial, check the lesson on the Visual Components Academy, and if the Download Files option appears, you can download the example files. In this tutorial, Paul will continue to explain the use of the delay and condition methods.
In order to do that, we have brought in 4 different components to the 3D world. One is a feeder, one is conveyor, one is LED light indicator, and one is a modified conveyor tracking base. So in our case, this tracking base doesn't actually work because we actually removed all of its signals and then we also emptied out its Python script. The idea over here is to generate a simplified conveyor tracking base on the later stages of this tutorial. So now let's actually generate some of its signals back. We know that we have a component path sensor over here that records a component signal and a Boolean signal. They're both set to null value because it doesn't have those signals. So first, let's begin with Boolean signal, and then with a component signal. When these two have been generated, we can click the component path sensor and then assign the component signal and the Boolean signal to that sensor. The next step would be then to visualize the whole thing. So when I now click play in the simulation and open up the signals interface tab and click the conveyor tracking base, we can see that this Boolean signal is flashing green whenever any of these cylinders go through it. Now, without having this interfaces open, we actually cannot see that, so the simplest way would be now to reset the simulation and then connect these Boolean signals of the tracking base and the LED light indicator to each other. Now we can close the Signals tab. And now we can clearly see that this LED light indicator will flash green when something enters the conveyor tracking base. The next step over here would be then to check its Python script. So let's double click the Python script to open it up. And then we should write some of its code back. And what we need to do first is to gain the handle of this Boolean signal. Here we can see that we already have some sort of code over here. So comp equals to get component is the same thing as if the user would click this conveyor tracking base over here. Then comp.findBehavior server controller is the same thing as somebody would click the server controller over here. So by that same logic, we can write something like Boolean signal equals to comp.findBehavior Boolean signal. And if the users are unsure whether they actually gained the handle properly, they can always print it out. If they did not obtain the handle properly, the print will give you a none type. And in order to see changes, the users always have to compile the script from the top left corner of this Python script window. As the output now prints out, Boolean signal object at some memory address, we're good to go. The next step would then be to make use of this onSignal event. So this onSignal event would listen to any signals that are assigned to this one specific Python script. And in order to assign signals to this onSignal event, we first have to click a signal here on the component graph. And on the right-hand corner, we get its, or right-hand side, we get its properties. Within these properties, we are very interested within this Connections tab. We can open up the Connections tab, click this plus icon, which will open this Add Connection Items, and then we will tell this signal that this Python script can now listen to this one specific signal. When that's done, we can actually go ahead and test this. So instead of define onSignal pass, we can write something like print signal.name and then some other text as well. Like so. And now again, in order to see changes, we always need to compile the code. When I now click play on the simulation, when this cylinder reaches the conveyor tracking base, we can see that it prints out this Boolean signal, which is the signal's name that triggers it, and then my text hello world. You can also see that it prints this exactly only once because the text within this output is exactly the same. So we have something akin to a filter guard that if the output recognizes that it's the exact same text, it will not flood your output panel. Okay, now that we know that we have gained the handle, we can now make the use of this onSignal event. We want to do a bit more than just print out text to our output. So what we could do here is perhaps stop the whole conveyor when something enters this conveyor tracking base. And in order to do that, we can make use of the conveyor tracking base's properties. So it already has something called parent behavior that has conveyor path in it. So we can actually gain access to the conveyor's path by this property itself. As we know how to gain access to the path itself, we can disable or enable it. So first let's test this by putting it inside this onSignal event. And we could also filter out signals because this same Python script can actually listen to multiple different signals. In our case, it's only one signal, but it would be a good habit to actually filter it out in some way. So filtering out generally happens with if clauses or if statements. So what this now tells us that if the signal's name is Boolean signal and its value is true, we can now do something. So in our case, we could stop the conveyor. Like so. So now we can again test whether this works, and again, in order to even see any changes, we need to always compile it. So now when the cylinder reaches the midpoint, we can see that the whole system has stopped. Now in our case, it would be very nice if we could simply tell the system to wait for 10 seconds and then turn the conveyor back on. But now we get into the issue of blocking functions, so basically anything that consumes time. If the function would consume time, it may only exist within this onRun function itself. So I could simply write something like delay 200 seconds within this on signal, but I already know that nothing really happens with that, but we can always test it. So we can do something like that, let's say after 200 seconds, put the conveyor back on. We can also trace the execution by enabling this second option over here. So now we know where the execution is going on within the script. And as always, we should always save it. And as you can see here, now it's basically stuck here on pause. And well, nothing really happens over here. This on signal does not really work because of this delay. This would mean that we need to change the whole system into on run, but that would also break some of its logic. So this is where the condition itself, a VC script method called condition, comes into play. So what we can do is to first generate a global list. Let's call it a queue. And then what we need to do next is to make a permanent while loop within this on run itself. And now we are going to use the condition itself. So this condition exists inside this VC script that we are importing, and it requires a function reference inside it. Now this my function doesn't really exist yet, so let's define it. And basically what we need to put inside this my function is something that returns true. But first let's modify some of this on signal event. So what we need to do first is to put something inside this queue. So if this signal name, Boolean signal, and its value are true, we can push in the component that the component signal detects. We can also put in anything else. But first I would say that we should put in the component there. Like so. And then we can append this component signal's value inside this queue. And now this queue will take in any component it detects within this tracking sensor. When that's done, we can check within this my function whether this queue has something in it. And if that's the case, we can then pop the queue. And it's important to pop the queue because otherwise this if condition or this if statement would always pass. Like so. And then as always, if we want to test something, it would be a good idea to print things out. Then let's compile and see what happens. As you can see here now, this whole system is stuck within this condition over here. And it waited until something went past this tracking base until it printed this out condition passed. Now in our case, we could always stop the whole system again. So in order to visualize this a bit better, let's stop and start the conveyor based off this condition. This will now stop it, and then we could write in the delay again back here. But instead of 200 seconds, let's just use 10 seconds. And then turn back the conveyor on. And I forgot to compile. But let's see what's going on now. So now we can see that it goes to the condition, it turns down the conveyor or powers it down, waits for 10 seconds, and then it will re-enable the conveyor. As we can see here that this delay only works when it's inside this on run, so we needed to move the whole logic inside. Now there's also other ways of doing this condition. So by definition, it again requires only a function reference, but users can also use anonymous one-line functions, basically lambdas. So we don't really need to have this my function over here, but we can write it in a simpler way. Like this. So basically what this lambda q means is basically this my function. It's practically the same, except it does not have this q pop. So if you write it like this, it's important to pop the q right after the condition. If that's not the case, what would then happen is that the lambda colon q would always return true. And this is practically exactly the same. That would be all for this tutorial.